Okay.
Is it possible to quickly go over the second way to do the multiplication?
Quickly, yeah, I guess so. Did you try looking at an example on your own? Did did you try doing an example on your own?
Yeah, but like, not really. Just, I mean, the old way I managed.
Well, what I'll do is, here, wait a second. I can't, why is my view not speaker? Oh, I'm on speaker view. There we go.
Maybe we could do in the meantime until more people show up.
Well, first of all, let's look at this. Oh, wait, I got to share my screen. I don't know why. Speaker view. I don't want to. Okay, share screen. There we go. And now, okay, that's the way I want it. Okay, so you see this? You can see my screen?
Yeah.
So basically, we take these two numbers, for example, and we look at the, I mean, I'm not going to do it exactly, but we look at this two digits and we say, oh, it's a 1, 0. So we go to this table and we say 1, 0 means to subtract. So we do that. We take this number and subtract it from the product. If you think about it, what are we doing here in regular multiplication? We're always adding these things to the product. We're taking this and we're adding it to the product. We're adding it to the product, but we're not adding it. We're not adding this number, this top number, many, many times. We're adding it, but each time it takes on a greater weight because we've shifted it left. You agree with that?
Yeah.
We shift it left, and then it has the bits become more significant bits, and we keep adding. So we are shifting and adding, shifting and adding. So all that we're doing here is the same thing in Booth. We're doing shifting and adding also, except we're shifting and adding and sometimes subtracting. And sometimes we're just shifting. So instead of it just being shifting and adding, it's shifting and doing nothing, which is if it's 0, 0, 1, 1. It's shifting and adding if it's 0, 1. And it's shifting and subtracting if it's 1, 0. If what's 1, 0? If the other number. So in other words, the first time we look at these two bits, and well, I mean, really, like I said, you have to add a 0. First thing we do is we add a fictitious 0 over here. And we say, look at these two. Those are both zeros, so we do nothing. So we just shift this number over. So our product remains 0. Now, next time, we look at these two numbers. According to our table, that means subtract. 1, 0 means subtract. So we take our product and we subtract this number from it. But this number has already been shifted on the previous time. After we subtracted it, we again shift it. Now we look at these two numbers. And we say, oh, 1, 1 means do nothing. So we just shift it. Then we look at these two numbers. And we say, oh, 0, 1, that means add it. So we take our number and we add it to the product. Now, the product previously was 0 minus this number after a shift. In other words, 0 minus, I think it was this. And now we're going to add to that this number, but with several zeros because we shifted it a couple times. So basically that's it. We just keep on progressing through these bits and looking at the pairs and doing whatever it says in this table. and miraculously we get the right answer. Is that good for you?
I think so. I mean, I'll try doing more questions later.
Take another example. Take, I have done for you the example, this example, which is 3 times 6. Do 3 times 7. See if it works out. Then do 2 times 6. See if it works out. Then try a negative number. A negative number, that's another thing. A negative number will also work, which is very useful for us.
We don't need to convert it. We could just do a negative number the way it is.
Yep, that's one of the big advantages of Booth. I don't have to convert the number from negative back to positive and then add 1 and then do subtraction. I can do addition with a negative number and it'll give me the right number.
What did we do for multiplication, like in a regular multiplication with negative?
That's what I just said. We put it back into, what do we do for negative ones? Yeah, we put it into positive and then remember the sign.
Oh, we're just noticing if
We have to invert
if
it.
one of our numbers was negative or both of their numbers were negative.
Yeah.
Okay.
Another, that's an interesting question. We didn't do multiplication. Maybe we did it.
Like that didn't seem like part of our algorithm before, but I guess it should be.
Well, if you just take a 2's complement number here, and we can try it out and do your regular multiplication, if you do -1 here, for example, that would be all 1s. So that means you'd have, I don't think you're going to get the right answer. You're going to get 0. Sorry, I'm writing in the wrong place. If you would just, I don't want to ruin what I have here. Let me get rid of this. Should be obvious that if we just would do, what is that? That's 3. That's 3 times -1. So what are we going to get? We're going to get 0, 0, 1, 1 plus 0, 0, 1, 1, 0 plus 0, 0, 1, 1, 0, 0 plus 0, 0, 1, 1, 0, 0, 0. True? We're going to do 4 times this. And I did 4. 1, 2, 3, 4. So if we add this all up, well, my columns are not aligned. If we add this all up, we're going to get, here, let's, just a second. We add this all up, what are we going to get? We're going to get, a 1 over here. True. And then we're going to get 1, 1, which is a 0 over here. And then we're going to get, well, we have a 1 over here, so it's 3. We're going to get a 1 over here. It's hard to see the columns. And then we're going to get a 1 over here. And that's it, because we only can take 4 digits. So, I mean, we could write, what number is that? That's, actually, that is -3. I think that is -3. Wait, is that -2 or -3? Might have worked.
Yeah, I think that is -3.
That's -3. Because -2, you sure, wait, let's see. Let me just, Yeah, that's -3. So we actually does work. Maybe I'm not sure if it does. What I understood is that it doesn't always work, but maybe it does. Maybe it just works with -1. I don't know. A good question. But actually, at the end of this today's lecture, I'm going to say that one of the advantages of Booth is that it works for for negative numbers without requiring inversion. I'll have to see if that's true. Anyway, that's regular multiplication. We saw Booth. Now I want to talk about a new topic. Wait, let me just make sure I didn't screw up my slide. Where is it? 1, 2, 3, 4. Yeah, okay. Okay, the proof of correctness of Booth. So we have to go. I asked the organizer of this course if we have to learn this, and we do. So let's learn it. We learned in the course Digital Systems that a number in 2's complement form can be calculated by the following formula. That's what you see over here, where n is the number of digits in the number, and n minus, in other words, if there's 7 digits in the number, or if let's say 4 digits, then n is 4. And n minus 1 is the first digit. So we're going to count the digits as n minus 1 and n minus 2 until digit 0. So it goes to go from 0, and notice if it's 4, it'll be 0 to 3, which is 4 digits. So this formula, did you guys see this in Digital Systems?
No.
I don't remember seeing something like that.
Me neither.
No? Well, if you had the course with Shmuel Weinman, you would have seen it, but let's look at it now. This is actually a very clever little thing, and it's going to be a way of computing. If you're given a number in 2's complement, I can always get the correct value in decimal without having to change negatives to positives or anything. So let's see how it works. Let's take the example. So first of all, what does it mean? This means there's -1 times the first digit, n minus 1. That's we said n minus 1 is the leftmost digit. The leftmost digit times -1 times 2 to the power 3. In other words, that number of the digit. If that's not digit number 3, then as if it's, remember I said my example is a 4-digit number, so that would be the 3 would be the leftmost digit. So this would be -1 times 2 to the 3rd. Plus, and now this sigma means sum, the sum of a series. Which series? The series that goes from n minus 2, in other words, the digit after this one, that would be not the 3rd digit, but the 2nd digit, n minus 2, all the way till 0. Notice where I, basically, you can think of it as a for loop, where I starts and is initialized at n minus 2, as long as until I reaches 0, including 0. Then do the sum of all the other digits, digit I, in other words, 2, 1, and 0, in our case. Our case is 4 numbers, so this would be 4 minus 2 is 2. So it'll be 2, and then 1, and then 0. Those are the 3 left terms in our series. So those 3 terms are all going to be the sum of them. And what are those terms? Those terms are digit I, which would be digit 2, or digit 1, or digit 0, times 2 to that power. If it's digit 2, then it'd be 2 to the squared. If it would be digit 1, then it'd be 2 times to the first power. And if it would be digit 0, it'd be 2 to the 0th power.
I think we did this formula. We just didn't write it out like that, like mathematically. We just learned how to do it like conceptually like that.
Okay, good.
Or at
Good.
least Jonah did.
So well, at least then you learned, or maybe you were reminded of how to understand a sigma. It looks complicated because it's a big, complicated letter, but it actually.
The sigma we learned in math and pre-calculus.
Right. Okay. But Now we're
Yeah.
using,
Quick question. So basically you're saying that you do the first one, like the far most left digit, and then you move all the way to the right and work towards your left.
doesn't matter the order, but we're just adding a whole series of numbers. But the first number, the key is the first number has a -1 in front of it. All the other numbers, and then we add all the digits with the first one getting a -1 in front of it. And the other ones, we just add them. So in other words, we're essentially adding the 3 digits on the right and then subtracting the first digit. But let's see how it works. Let's see an example. Let's
It's
take,
basically the same thing. It's basically the same thing as normal binary, except the negative.
yeah. It's basically the same thing as normal binary except the negative, but let's see how it works. Let's see the example 7. 0, 1, 1, 1 is 7. Notice I have to write the 0 here. Otherwise, it's not 2's complement. 2's complement means that it's got a leading 0 when it's positive. Wait, I hear some background noise. Mute yourself, please. Thank you. No, mute. Okay, somebody's talking. I can mute you, but then you can't talk. Anyway, please mute yourself if you can.
If you mute us now, we could just unmute ourselves when we want to talk.
Yeah, you can?
Yeah.
I thought I have complete control.
You do, but then if you just mute us, then we should be able to unmute ourselves.
But I don't even see who it is. All right, anyway, fine. I'm just going to continue. It's not too bad. No, it is bothering me.
You're all muted.
They're all muted? Okay.
A mistake. Sorry, there was the background.
Yeah. Okay, so here's an example to show that this is true. So remember, we have to have a 0 in front for it to be 2's complement. So we do -0. In other words, that's what it says. -1 times 0 times 2 to the third, because it's 4 elements, so it's n-1, 2 to the third. Well, that whole thing, -1 times 0 times 2 to the third is 0, so I wrote a 0 over here. Now the next one is 1 times, because remember, the digit is a 1 over here. So I'm going to do a 1. Instead of 0, it's going to be 1 now, times 2 squared, because I went up, or whatever, however you think of it. I went down by 1, or, yeah. It was 3, now it's 2. So that's 2 squared is 4. Plus 1 times 2 to the first, which is 2. So I wrote a 2 over here. Plus 2 to the 0th is 1. So 4, 2, 1 equals 7. Now, let's see if it also works for a negative number. -3 is 1, 1, 0, 1, as we just saw. So let's see if it works. So again, we're going to take -1 times this 1 here. So that'll be -1. -1 times 1 is -1. Times 2 to the third. So that's going to equal 2 to the third is 8. Negative is going to be -8. Then we're going to say plus. Again, there's a 1. So 1 times 2 squared. 2 squared is 4, so we're going to have 4 here. Plus 0 times 2 to the first, well, it doesn't matter, it'll be just 0. So plus 0. And then the last one is a 1, so it'll be 2 to the 0th times 1, which is 1. So we get -8 plus 4, which will be -4, plus 1 will be -3, -3. So I just demonstrated, I didn't prove, but I demonstrated that this is correct. Notice that was not a proof, that was just a demonstration. It's hard
What
to
does this have
imagine.
to do with Booth?
This, because you're going to see. I'm giving you a few pieces of information. We're going to prove the correctness of Booth. We are now proving that Booth will always work. First thing we have to do is understand how to represent a number, because we need to be able to represent the number in terms of a series in order to see if the multiplication works. I'll show you. You'll see. So now we're going to do two restatements of the product A times B. Let us assume that we have two numbers, A and B, and they're both in the 2's complement format. And they're each of the same length n. We can write in terms of the previous formula and thus produce the following. We can say that A times B equals, this is A, this is all A. This whole thing is A times B. True? So far, so good. We just proved that this is A, that this represents a number of length A, of length n. This is a number of length n, the value of it. And B is also that, is the number of length n, but it's a different number. So A times B equals this whole thing times B. So let's keep that in mind. Agreed? Somebody?
With that formula, converts it to 2's complement?
No, we're just saying, no, it's nothing. This is saying, take A and put it into 2's complement. Yeah, I guess you're right. Take A, put it into 2's complement, apply to it this formula, and you're going to get the decimal equivalent. So this is the, assuming that this number is in 2's assuming that A is in 2's complement, I now have represented A, this whole thing, as a decimal number. That's what we learned. We just showed that
B is not in decimal.
B is also in decimal.
How? We need to convert it to decimal first, no?
No, it's, oh, I see. B is not in decimal. You're right. Fine. But it doesn't matter. B is a number. Doesn't really matter what format it's in. It's a value. Math will work the same on, in other words, however we do times, I don't know, but I mean, assume that it's a decimal number. I mean, you're right. I said there are two numbers in 2's complement, but they're numbers. They're the value 7. This is 7 and this is 6, then this is 6. It's that value. You're right. Technically, it's also in 2's complement, but it doesn't really matter. If this is true, then this must also be true. If A times B is something, if that's computable, then this has got to be computable since this is A. All right, that's the first step. Let's go to the next step. According to Booth, we can write A times B like this. Now, remember, in Booth, we define, this is a tricky thing here. We define A of -1 as equal to 0. What do I mean by that? Remember way back in the beginning of today's lecture, I went over here when I wanted to show you how I would do this in Booth, and I said, well, I got to first add a fictitious digit over here, because that's the way Booth works. First, he assumes a 0 over here, so there's a fictitious digit, and it's really 0, 0, and then you look at this, and then you look at this. So we have to talk about digit -1, because this is digit 1, or this is digit, sorry, 0, and digit 1, 2, and 3. So if this is digit 0, then this digit that's not there is digit -1. So we need to talk about that. We need to, relate to it. We need to include it in our formula. So we're defining A -1 as 0. So we can rewrite Booth like this. B times A. Now this is true. We've sort of proven, we haven't really proven, but we've demonstrated this is true. And this is also going to be true. Once, I'm just showing you where we're going. If I can show you that this whole bloody mess is the same as this, then I've proven what I wanted to prove. Because this is A times B, not using Booth. This is just regular, this is just A times B. This is A and that's B. And if I can show you that this, if I take this Booth thing, I can turn it into this, then I've succeeded in showing you that the Booth method will produce me the same result as regular number multiplication. So let's go slowly. So why is this Booth? That's the real question. This is Booth. Well, notice that I did B times A, where let's assume that, I don't know why we switched the order, but that's the way he did it. B is, let's say, the B is the I don't know. It's either the mantis. I'm trying to remember if it's the multiplicand or the multiplier, but it's one of the numbers. And what is this a minus 1 and a 0? So a minus 1 is the digit that we invented. And a0 is really the first digit. And that represents location 2 to the 0th. So if you remember, here, let me go here. If you remember, what does Booth say to do? Right? Booth says that if it's 1, 0, subtract. Well, if we added a 0, so let's go to our thing. If we added a 0, if this was a 0 and this is a 1, what are we going to get here? We're going to get 0 minus 1, negative 1, which means it'll be negative 1 times 2 to the 0th power, which means I'll be subtracting that digit. Furthermore, what else did Booth say? Booth said that if it's a 0, 0, then I don't do anything. But if it's a 0, 1, then I don't do anything either. So that's the other possibility. In the first case, it's either a 0, 1 or 1, 0 or 0, 0. Then I won't do anything. So if it's, what does it mean 0, 0? If this is 0 and this is 0, then 0 minus 0 is 0. So 0 times 2 is 0. I don't add anything. You see how I don't add anything? Because I didn't add this. This doesn't get added to anything because this 0 times 2 times b, the whole thing will be 0. So if they're the same, I don't add. And if it's a 0 and a 1, then I'm going to subtract 1 times whatever b is. B is the actually, if you think about it, b is the multiplicand. Yeah, b is the multiplicand. Remember, that's what we decided in Booth. What do we do with the multiplicand? Do we add it to the product? Do we subtract it from the product? Or do we just not do anything with it? So by writing this, I'm writing that 0 minus the first digit. If the first digit is 0, then do nothing. If the first digit is 1, then subtract the multiplicand. Because this is 2 to the 0th was 1. Subtract the multiplicand. Hey, that's exactly what I'm supposed to do in Booth. What about the next digit? What about the next pair? It says examine the next pair. Well, the next pair could either be one of 4 possibilities. What? Yeah. Just when you do open, just say open in, instead of just clicking on it, you say open in Google Docs. Sorry, I have to help my son there. Okay, so that's the first digit. And again, this is the second. Now we have all, in the first case, we only had 2 possibilities because we always know that the a minus 1 is 0. But here, a1 and a0 and a1 could be any of the 4 possibilities. And I'm going to get exactly the right result here because I'm going to say, let's do the plus. Let's assume it's the plus case. What's the plus case? The plus case is it's 0, 1. So let's assume that it's 0. Wait a second. Let's remember which digit is 0. Which plus is that the lower digit is a 1. So if the lower digit is a 1, that's this digit, 0. And the next one is a 0. 1 minus 0 is 1. So I'm not going to nullify this by multiplying by 0. I'm not going to multiply it by negative 1. I'm going to multiply it by positive 1. So that means I will, yes, go ahead and add the multiplicand. But I won't add the multiplicand as it is. I'll add the multiplicand times 2. Well, guess what times 2 does? Times 2 shifts it left. Similarly, the next digit. I'm going to do the same process each time, subtracting the right digit, the left digit from the right digit. And I will get either a negative or a positive, which will tell me whether to add or subtract. The multiplicand shifted another place. So does everybody see that this is Booth? Or does somebody have a question that this is not Booth or not understand something? I need either yes or no. Otherwise, I think you're all in the other room. You're all in the other room.
It's a very complicated formula.
It is a complicated formula.
We will need some practice, but for now I have no questions.
It's very funny. It's also, I want to see it. Oh, was the bee ready singing? But go out. I've got to teach still. It's a complicated formula. I agree. But, I'll tell you, if you look at it, if you think about it for a while, it starts to become clear. I didn't explain the continuation. The continuation is just more of the same. It's just the same, except instead of writing 2, I wrote 1, I wrote 2. Then instead of writing that, I write I, and then I plus 1, etc., until eventually we come to n minus 3, n minus 2, and finally n minus 1, and I've reached the end. I've reached the last element. So it just continues on. So actually, all you really have to understand is the first term. This is essentially, A times B is essentially a set of terms, this term, and all of them are the same. They're of a certain format. The right digit minus the left digit times 2 to the power of whatever digit I'm on times the multiplicand. And just keep doing that over and over again. And that's what for you, because I thought you wanted them. So it just keeps repeating. So it shouldn't be too complicated. But let's go on. Let's go on. You can look at it. Actually, this is not on the web yet. It's not on the Moodle. At the end of Shir, I'll upload it so you can look at it.
This isn't this the Booth presentation?
Yeah, but the version that you have up there doesn't have this part in it. I updated.
Oh, so if I download it last night, I should re-download it?
You should re-download it after Shir because I haven't yet uploaded this yet.
Okay.
I don't think so, unless you looked at it and you saw this was there.
I wasn't looking this far. I only looked at what we did, but I don't remember if there's something after that.
I don't think I put this up yet, so I'm going to put it up after class. Okay, let's go to the next slide. So this I'm just saying, why does Booth lead to this statement? And I basically just explained that all to you. I'm just writing out in words here. But I showed you that this is the shift left. Because when I multiply anything by 2, I shift it left.
I'm confused as to how this is more efficient than normal multiplication.
Well, we're going to get to that's the last slide of today's presentation. If it is more. First of all, who says it's more efficient? I'm not sure. Secondly, I'm not interested in that right now.
Otherwise, I'm assuming we wouldn't be learning it.
No, you said either yesterday or at some point.
It is more. Why is it more efficient? Well, you can look up Booth on, type into Google, why is Booth more efficient than regular multiplication? And you will see some answers. One of the answers is that the computers, it's faster for them to do shifting than to do anything else. Just the way the hardware works. And this has more shifting, although actually we saw that regular multiplication also has shifting. We'll discuss exactly it, but it's a good question. Is it more efficient? As far as that's why we're learning it, well, we're learning it because this is actually how computers do it. And we're learning computer architecture, so we should learn it. Even if it would be less efficient, we should learn it because This is how computers work. They don't do the other efficient. Presumably, it's slightly more efficient. But this is, in point of fact, how most computers work. So that's why we're learning it. Whether or not it's a good idea. Presumably, it is a good idea. But even if it weren't a good idea, we would still learn it because that's the way they work. And we're learning computer architecture. So this is just in words. I explained to you again what I said over here when I tried to show you what these different elements are. Now let's go to here. So now, up to now, it's not a proof. We just said that A times B is this, and A times B, according to Booth, is this. So now what we've got to do is say, is this the same as this? If it is, then Booth is the same as regular multiplication. Then Booth is multiplication. Notice this is multiplication because this is A times B. If this is, notice there's a times here, there's a times here, there's a dot here. So the same times here is the same times here. So this is multiplication, and this is what Booth claims will produce the same as this. So let's see if it does. So that's the proof. Let us show that the Booth statement equals the 2's complement formula. So let's take that Booth statement, here it is, and we're going to rewrite it. We're going to do a little math. But this part should be easy, basically. We're going to take out the B from the whole thing. Let's say I took the B out from the whole thing. So how do you, so if you take the B out, then you're left with 2 to the power 0 times A minus A plus A minus A times 2 times, you can take out, each term has a B in it. So I'm going to take out the B's. That's what I do over here. So I get minus A times 2. Why did we get this? Why is it just minus A? Well, that's tricky. But since we have assumed that A to the 0 is 0, that's what we've written here. We've defined A to the 0 is 0. So if this is 0, then this is just minus A. So we can rewrite it as minus A times 2 to the 0 plus, well, let's look at this thing, plus again, well, we're going to sort of regroup. We're going to spread this out. This 2 times B, we're going to attach it to this and to this. And then we're going to take the B out of it. You can work it out on paper, but you're going to get this expression. A to the 1 times 2 to the 1 plus A to the 1 times 2 squared. Anyway, it's going to keep going. Notice it's a minus. It always starts with a minus and then a plus. A minus and then a plus. And we keep going. And now we say, notice that the pairs of terms in the parentheses are equal to the form. So look at each of these parentheses here is equal to the form minus A of I times 2 to the I, right? Plus A to the I times 2 to the I plus 1, plus 1. So we can take that term and rewrite it as minus A times 2 to the I plus A to the 1 times 2 to the I. Because what does it mean, 2 to the I plus 1? It means 2 times I plus 1 is, I is, let's say, 3, plus 1 is 4. So it's 2 to the 4th, but I can rewrite that as 2 to the 3rd times 2. So that's what I do here. I reduce this back to I and take out a 2 and put it in front. So once I did that, I now see that there's a to the AI times 2 to the I in both parts. So I can take it out. And then what I'm left with is negative 2 sorry, is -1. This becomes -1 plus 2. So -1 plus 2 is 2 minus 1 is 1. So each of these elements turns into a of I, a at location I, times 2 to the I. So I can just get rid of all of these things and replace them by this thing. So let's go back to our Booth statement and substitute everywhere this for every time we saw a minus a to the I plus a to the I plus 1. Now there's a minus a to the I plus a to the I plus 1. We're going to go and substitute all these for it, and we get the next slide. So we get all this, and then this becomes that sum that we saw before. This becomes that sum that we saw at the beginning. So we've proven that Booth is equivalent to the normal formula of 2's complement of B times A. In other words, we are back to the 2's complement formula. So we've shown that it equals. I mean, I didn't go through how I got all these things. You'd have to write it out you'd have to write it out. You have to process it, and see that this is correct, but it is. Now you asked about Booth efficiency. So let's think about this. In ordinary multiplication, for every one, we need to do an add and a shift, right? If there's a 1 on the bottom number, then we've got to add the top number to the product and shift it left. Every time there's a 1. So if the multiplier has a set of 1s or a set of 0s, so what does Booth do? Booth, if you look at it, Booth, if it's a 1, 1, it just does the shift. It doesn't add. Or 0s, it just does the shift. So here's our main efficiency. Here's our one efficiency that we get. But it's only an if. If the multiplier is just a set of 1s, it's a whole lot of 1s, then we're just going to keep shifting, and never adding until the last one, where we have a 0, 1, and we'll add. But if it's a set of 1s, we'll just shift, and not have to add at all. So that'll be much more efficient than regular multiplication, where we shift and add. Because here we just shift, we don't do the add. Also, if it's a set of 0s, like 1, 0, 0, 0, 0, 0, all those 0s will just shift. Well, actually, in the multiplication, it also will shift. It won't necessarily add, depending on how it's written. That's a check. But yeah, it'll be the same if it's a set of 0s. But if it's a set of 1s, it'll be more efficient. But not just a set of 1s. Anytime there are 2 1s in a row, it'll be more efficient. That every time is a 1, 1 progression, Booth will be more efficient because it'll just do a shift instead of doing a shift and an add. So Booth will be more efficient or equal to, because Booth will only do a shift, whereas the regular method will shift and add for every one. Okay, that's one efficiency of Booth. But what about if we have a set of alternating 1s and 0s, like 0, 1, 0, 1, 0, 1, 0, 1, or 1, 0, 1, 0, 1, 0? So then on both of those cases, Booth will always do an add or a subtract. So Booth will do twice as many add subtracts as the ordinary multiplication, because the ordinary multiplication will look at the 0 and just do a shift. And but when it sees a 1, it will add. It'll see a 0 shift, 1 add, shift, add, shift. So, but whereas Booth will do, this is like the worst case scenario for Booth, because you're gonna have to do a subtract and then an add and then a subtract and an add. He's going to keep doing adding and subtracting and never just shifting. So in this worst case scenario, clearly the multiplication will be better than Booth. And here's the sentence that we were talking about before. Furthermore, for negative numbers, the regular method must invert the number and add 1. this step is not needed with Booth. I just wonder if that's true. I mean, I didn't make that up. I translated this from the book of the course. So until now, I thought that was true, but maybe it's not. We have to work it out. If you see if regular multiplication works with 2's complement. Maybe it does. Maybe it doesn't. You know what? Maybe it doesn't because of the frame, of the size of the frame. Oh, you have to have a product that's twice as big. No, I don't know. I have to think about it. Anyway, multiplication always doubles the size of the frame. The size, if it was 8 digits by 8 digits, the result would be 16 digits. I'll have to think about that more. But according to this statement, I have to do some tricking, do some special manipulations if I've got a negative number, and in Booth I don't. So overall, Booth is somewhat more efficient. I'm not sure I'm convinced, because, I mean, it's certainly more efficient if there's lots of ones that are next to each other. And how often does this worst case scenario happen? I mean, it's not going to be like this. It's going to be, a normal case will be something like this. There'll be some ones together and some alternating. Now in this, I mean, take a case like this. What will Booth do? What will Booth do and what will multiplication? Multiplication will do 1, 2, 3, 4, 5 adds. Booth will do how many adds subtracts? It'll do 1, 2, 3, 4, 5. The same. Everyone sees that? Because in Booth it'll be 0, 1 is I don't remember if 0, 1 is an add. 0, 1 is an add. Then it's a 1, 0, subtract. Then it's a 0, 1, add. That's 3. Then it's a 1, 0, subtract. 4. Then it's a 1, 1. Then it's a 1, 1. And then it's a 0, 1. That's 5. 0, 1 is again an add. So that's 5 adds, subtracts, plus all the shifts. Multiplication will have also all the shifts, but 1, 2, 3, 4, 5, same. So it'll be exactly the same in this case. And that's kind of sort of an average case. In this case, Booth will be worse. But in some cases, Booth will be better when it's lots of ones in a row or lots of zeros in a row. So is it more efficient? Not sure. But according to what he wrote, it's more efficient. If you go to the internet and you type in is Booth more efficient than regular multiplication, and why Booth multiplication is faster, he says Booth's algorithm is a multiplication algorithm that multiplies 2 signed binary numbers and 2's combination. Booth used a desk calculator that were faster at shifting than adding. Okay, and created the algorithm to increase their speed. Booth's algorithm is of interest in the study of computer architecture. So it's of interest. But I don't understand this statement, because Booth uses they were faster at shifting than adding, but you do shifting also with regular multiplication. And you do adding. So either way, you do shifts and adds. I don't see why Booth has more shifts. It has less adds, maybe, but maybe. Depends on the number. You can look, there's a Wikipedia page, Booth multiplication. There's actually an improved Booth, which we're not learning. But this is like we learned the basic Booth, but there's actually articles have been written on it. I saw an article from the 90s. Somebody wrote an improved version of Booth. So it's still of interest. I don't know. you know, to prove that it's more fast, is a good question. Is Booth, let's try a different search. Is Booth faster? Is that what we already saw? Yeah, we're not getting a good answer. It's a good question. You can try to figure that out, why it's faster. But the conclusion of my limited research is that it's somewhat more. That's all I can say. It's somewhat more efficient. You know, given average cases, it might be the same. In some cases, it'll be better. In some cases, it'll be worse. That's what you really need to know for the exam. Which cases it's better and which cases it's worse. Because when you understand, if you're able to answer that, then you're able to explain, then you show you know the algorithm. Kind of, unless you just memorized it. But this case is the worst case scenario for Booth. The best case scenario would be all ones. All right, we'll stop here. Next time we'll do chapter 9. I'll upload this and I'll upload the slides.
Thank you.
Sure.